Okay, hello and welcome to the next Tuesday seminars here at the Warsaw University Astronomical Observatory. Today our guest is from Torun, and we have a privilege to have a guest in person, Cezary Migaszewski. He did his studies in Torun and is now working at the University of Nicolaus Copernicus in Torun, and he's going to tell us about the planet 9. And dark matter.
Yes, thank you very much. Thank you for the invitation. And hello, everyone. I'm going to talk today about Planet 9, the hypothesis of Planet 9, also about the hypothesis of dark matter. And I'm going to show that these two hypotheses are connected with each other. And if one is true, the other has to be true as well. And what is the connection? Because they seem to be independent of each other. What is the connection? The connection is gravity, because both dark matter and Planet 9, the ninth planet in the solar system, they are postulated on the ground of their interaction, gravitational interaction with visible matter. Yes, in both the cases. So gravity is the link, and the outline is here. First, I'm going to speak about reasons why people think dark matter exists, and then about alternative explanation of various phenomena. Next, I'm going to say why people think that in the solar system there is another planet. And again, I'm going to show that this can be the phenomena, the dynamical phenomena in the solar system can be modeled with the help of, there is an alternative explanation, okay, related to modified gravity. Yes, and at the end, I'm going to discuss how these two hypotheses are connected and what are the conclusions. First, the history of dark matter studies. The history is quite long. First time the necessity of dark matter was pointed out was by Oort, and he noticed that stars above the galactic plane, their kinematics requires some more mass. Yes, but shortly after that, it turned out that it's enough to add gas, dust, and low mass objects, and it is enough. So it was fine. But 1 year later, Zwicky, in 1933, he studied the cluster of galaxy cluster, comma cluster, and he noticed that the dynamical mass is significantly larger than the observed mass, even assuming relatively high mass to light ratio. So there was a necessity of some additional mass. And the most famous indicator of dark matter is the rotation curves, of galaxies, right? First, M31 was studied, and Babcock noticed that there is no Keplerian decline in rotation velocities in the outer part of the galaxy. And then when radio astronomy was used, radio telescopes were used, it was confirmed that the flat rotation curves for this galaxy and other galaxies, they reach far beyond the optical image, optical galaxy. So this is the early history, but there are some other reasons why people think there is some dark matter. There are dynamical reasons, and when we take this galaxy, most of its kinetic energy is due to rotation. So we say that such systems are rotationally supported. Only small fraction of the kinetic energy is deposited in random motions. And so, and these kind of systems are called yes, called. And when we take mass as we see it, and we run n-body integrations, just simple integrations, we see that rapidly such a system, this galaxy, which is dynamically cold, evolves rapidly into dynamically hot system. So pressure supported system. So this, and people try to figure out what to do in order to stabilize these galaxies, because we see these galaxies, they exist. So it's obvious that something is wrong. And so at first there were some attempts in which gas was added in order to cool down the galaxy, this galaxy, but it was not enough. And then dark halo was proposed. Very massive halo, which stabilizes the disk, and the mass of such a halo is much, well, the halo is much more massive than the disk, and there are some cosmological indications of that most matter in the universe, most matter in galaxies is dark. Probably most matter in the universe is also dark. So this is this dynamical argument. And there is some part of dark matter was actually found, which is hot gas in galaxy clusters, which could be observed in X-rays. But it was not all. Still, some mass is missing, but there are some other techniques. I haven't mentioned this. The study of Zwicky, he compared the virial mass actually. Yes, he used the virial theorem in order to infer the dynamical mass. So it is one approach, but there are some other, like modeling the temperature of gas, feeling the potential well of a cluster, but also gravitational lensing by a cluster of some more distant galaxies whose shape should be elongated. And these two methods, together also with the virial method, they all give results which are in agreement, in good agreement. So it's all fine. But still, some mass is missing, even though there is this gas. And also there are some cosmological arguments. Cosmological arguments for dark matter. One is the nucleosynthesis of light elements, because their abundances, they depend on the density of baryons. And it was shown that this density of baryons required in order to achieve such abundances as we observe them now are much smaller. The density is much smaller than the critical density of the universe. And because it is much smaller than the critical density, the rest of the density should be non-baryonic. So this is the result. Not only that there should be some mass, but also that it should be non-baryonic. Another argument is from the structure formation studies. Initially small perturbations in the early universe on the way of gravitational instability. They lead to structures we observe now, like galaxies, clusters of galaxies, and so on. And there was a problem in growing such initially small density perturbations. And this problem was again solved by adding some mass, which is non-baryonic. Seems to be quite strong arguments for dark matter. And this plot, actually it is only here because a talk with dark matter in its title wouldn't be a proper dark matter talk without such a plot, right? It's only the only reason. Most of the mass energy budget is dark energy. Most of matter is dark matter. Only some percent of matter is ordinary matter. Okay, so we have this clear picture, this standard picture, cosmology. Here are again the arguments in favor of dark matter, the arguments I just described. And so the question is, why doubt it? Why doubt it if everything is so clear? You see that all the methods, for instance, the methods of determination of mass in clusters, they seem to be independent somehow, and they all give consistent answers. Also, some other arguments like dynamics of galaxies and so on, it also gives consistent results. So why doubt it? There are two reasons. One is obvious, because dark matter has not been detected yet. This is what people who like dark matter will say. Yet it doesn't prove anything. Yes, it cannot be falsified this way because we don't know the nature of it. Okay, but the other reason to doubt is that all these arguments, they seem to be at least partially independent one of each other, one of another, but they actually are the same argument. This is the same argument actually. Because all these studies showing that there should be some extra mass, all these studies rely on the same assumption that we know gravity. Gravity is Newtonian or Einsteinian, depending on if necessary, we go to general relativity. But we don't know it, right? We don't know what gravity is in this scales. We don't know it. And several times I used a term, I said that there is some matter needed. There's necessity for extra mass, but it is just a shortcut, obviously, because what we need is not mass, it's gravitational attraction, right? So it can be achieved either by adding mass or by modifying gravity, obviously. Okay, so let's see how this alternative explanation looks like. Modified gravity. It's quite old, actually my age, exactly. From Milgrom, 1983, he proposed that in order to achieve flat rotation curves, because it was his goal, it is enough to modify gravity in such a way. There are actually two ways which are equivalent. Here is the gravitational acceleration, the Newtonian acceleration. This is this acceleration, modified acceleration. And here is some scalar function of the magnitude of this g divided by some universal acceleration a0 of the order of 10 to minus 10 meters per second squared. Or it can be done like this. This unknown g is on the left, and everything known is on the right. And these functions, they are not part of the theory. They can be taken somehow freely. We don't know what these functions should be, but we know exactly what they should be, but we know their properties. For x, which is the argument, much higher than 1, so it means strong acceleration, strong gravity field. This function should go like 1. And then we have normal Newtonian gravity with the rotational circular velocity like 1 over Earth's square root of r. And in the second regime, when x is small, it should increase as x. And the gravity acceleration, this gravitational acceleration looks like this in this limit, and the velocity, the rotational velocity is constant. These functions, they have different, these are the limits, right? But it can be the particular form of this function. It cannot be referred from the theory. Yes? Also, this quantity A0, it has to be obtained from observations. Okay. But this transition function, just to say about this, on the bottom right, there is this parameter alpha. If alpha is larger, it means the transition is more rapid from Newtonian regime to Milgromian regime. If alpha is small, it is more smooth. Okay. But this is a simple thing, and naturally it was a good tool to explain rotational curves. But what about other phenomena? And actually, we are speaking here about predictions, not explanations of MOND. One prediction is that because the galactic rotational curves, they become flat in a low acceleration regime, but the value of this velocity, it depends like this on the mass. Yes. So v to the power of 4, this is this asymptotic velocity, is proportional to the mass. And in 1977, Tully and Fisher, they noticed that there is a correlation between the galaxy luminosity and the width of the H1 line, which can be translated to velocity dispersion or this asymptotic velocity. Yes, so they noticed that there is this correlation, and this coefficient beta was not well known at that time because there are not many points here. And in some newer studies, it was shown that this coefficient is about between 3.5, 4.5, depending on the band. And this is exactly what it should be if MOND is right. Yes? So at that time, so it can be treated as a prediction of MOND. Yes, for MOND it is exactly 4 if mass is proportional to the luminosity. Yes, because here is luminosity, and if we put mass here, it's exactly this relation, this blue line. Oh, first prediction. The MOND was not designed to do so. Yes, to explain this relation. Another prediction of MOND is the following. We see that this is the Newtonian acceleration, Gn. Well, naturally, it is G times n in the radius of r over r square. And it is like G, the gravitational constant, times surface density. Surface density. And this is, you see, G times sigma is like Gn. If Gn is small in comparison to A0, it means this Milgromian regime, this low acceleration regime. And what it means that if we find galaxies with low surface brightness, because again, if we translate surface density, mass density, into the surface brightness, if mass is proportional to luminosity, then we see that for low surface brightness galaxies, significant part of such a galaxy, or even in some cases, a whole galaxy, is in the MOND regime. Yes, it is a prediction. At that time, it was not known that many galaxies of this sort were not known. But later, when more galaxies were discovered, and actually not necessarily discovered, measured their velocities, it turned out that indeed low surface brightness galaxies are, in the language of some people say Newtonists, assuming that gravitation is Newtonian, the conclusion was that low surface brightness galaxies are dark matter dominated. Yes, but it was actually a prediction of MOND that they should look like they are dark matter dominated because they are in the MOND regime. And again, MOND was not designed to model this kind of galaxies, but the flat curves, flat parts, not this thing. There is another prediction, modified gravity, which is there are some regularities in the deviation from acceleration stemming from mass distribution, and the acceleration which is measured. Actually, it is centripetal acceleration. When for a given galaxy, we can measure its rotational velocity, the distance of a given point. So we've got centripetal acceleration. We can measure how much light is within a given radius. It'll be translated for some reasonable mass to light ratios into mass. And we see that if MOND is true, because it is something universal, right? Let's say the dark matter distribution can be different depending on parameters, but gravity is something universal. Like for Newtonian gravity, it cannot be like for one system is 1 over r squared, or some other 1 over r to the other power. Yes, it has to be universal. And the prediction of MOND is that for a group of galaxies, many galaxies, for each galaxy there are several points in which we can measure both acceleration due to mass and acceleration taken with centripetal acceleration. And we can see that there is a nice correlation. There is some deviation for accelerations around this value A0. And MOND gives such a dependence for reasonable values of this alpha, which this alpha is in this transition function, right? And A0 of this value. Okay, so these are the predictions, and we see, but this simple prescription of modified gravity can be used only to model a test particle around a static object, one body, let's say, its gravitation and some test particle, and that's all. If we want to have n-body simulations, for instance, to model dynamics of galaxies or some other things, we need something else. Yes, this was too simple. There were several problems, theoretical problems with this model, and this model was generalized, and it is like you see. This is this formula: mi times g is gn. When we for g we put the gradient of potential minus this, and we compute the divergence. We see that there is an equation of this form, which is a modified Poisson equation. If we put here what is on the right side of the Poisson equation. We will see in a minute. It's just like the Poisson equation, but slightly modified, and it can be used for dynamical systems. Yes, for a given distribution of mass, we can compute what is the gravity, like for the standard case. In another approach, it is like G, this unknown, is on the left, and everything here is on the right. The same thing, and we will see the Laplacian of the potential equals some formula here. Yes, some formula. It is much more convenient, practical, better for practical purpose, because here you see there's the potential, Newtonian potential phi n. It is given by the distribution of physical mass, and when it is given, you can compute the potential of this modified potential. Yes. Okay, and let's see how to interpret this equation. We see in the top how this equation looks like, and the standard Poisson equation, yeah, the Laplacian of the potential equals 4 pi g times the density of matter, physical matter. And we can do the same thing with our modified, this is for the potential, Newtonian potential, yes? But we can write the same form for the Newtonian potential, and we see that there is, again, 4pg times some different density, yes? And we can express this density. Actually, maybe it's not that important here. This formula at the bottom, this density equals, can be written down as a sum of physical density and something else, which is interpreted by Newtonists as dark matter. But in the modified gravity theory, it is called phantom mass. Just to say that it is not real. It just results from the modification of the Poisson equation. Okay, and this theory, this generalized, let's say, modified Poisson equation, can be used to study dynamical systems like galaxies, like galaxy disks. And it was shown that because it was this problem with the stability of disks, as you remember, yes? And the extended halo was added in order to stabilize the disk. When you treat the disk within the modified gravity, it works well. Yes, there's no, well, it can be, there are two things actually. The maximal stabilizing effect of MOND corresponds to a halo of a mass of 3 disk masses. So it is max what we can achieve from MOND. But in general, in MOND, galaxy disks are more stable. But in the Newtonian regime, because we have galaxies of very high surface brightness, so high accelerations, there should be unstable, because it's not MOND regime, it's Newtonian regime, so it is a problem. What about them? We observe these galaxies of very high brightness, surface brightness, right? But maybe not necessarily, because when we translate this critical surface density, which equals A0 over G, it is exactly the same. Just I will show you. It's exactly this. Okay. It is like 860 solar masses per parsec squared. This is this critical density, surface density, and it can be translated into the surface brightness. It's like 19 plus, and this is the mass to light ratio. And the observational fact is that we don't observe galaxies of such high central brightness densities, like 21, 22 magnitude. What we observe is is for magnitude greater than this value. This is what we observe. So again, according to MOND, such high surface brightness galaxies should be unstable, and we actually don't observe them. I cannot. Okay, one moment. This is it. Okay. Well, there are some other let's say phenomena modified gravity can explain. It's like for pressure supported system, for given object, we can compute typical accelerations like this typical velocity square over r, typical acceleration, and we can see for objects of different scales, from globular clusters up to clusters of galaxies, that for all of them, the typical accelerations are very close to A0, yes, for objects of very different scales. And it is what is expected from MOND. There is one problem with MOND, because for galaxy clusters, when we compare the observed mass versus dynamical mass, and we have several galaxy clusters, we see that for the Newtonian gravitation, there is a difference between these two masses is a factor of 7, let's say. 7 dynamical mass is 7 times bigger than the observed mass. For MOND, it is reduced but not eliminated. So it is around 2, this factor. Still, 2 times more mass is needed. However, these results are quite old, actually, and since then, some better estimations of this A0 acceleration was obtained. So I'm not sure if someone made this analysis again, that the results would be the same. I'm not sure, but there is some problem, some problem of MOND. Okay, but what about the second protagonist of this talk, Planet 9 or Planet X, as some people call it? Actually, what I was speaking about just a moment ago, this battle between two different paradigms, like modified mass versus modified gravity, is something that it's actually just saying. It is not the matter in galaxies, galaxy clusters versus MOND. The history is older. When we look at the problem of the history of Planet X, we see that there were a few examples of this competition between two different approaches. And in the first case, it was the history of the discovery of Neptune, very well known, I'm sure. And we had some unexplained perturbations of Uranus, and some new planet was proposed, and it was actually predicted where it should be, and then discovered it was Neptune, right? And if we use a football terminology, we would say that this match between the two approaches, modified mass scored a goal. Yes, so it's 1-0 for modified mass. But the match continues, and there was another situation with the perihelion of Mercury, also very well known. Some anomalies in its precession. Again, some planet was proposed, even named Vulcan. But this time, it was not detected. Yes, but the solution to the problem was different. It was general relativity, as proven by Eddington and his expedition. the solar eclipse. So it was an equalizer. So it is 1-to-1. Yes, modified gravity stored the goal 1-to-1. There was one more situation. It was there were some problems with the orbit of Uranus. Still, there were some inconsistencies, and again, some additional planet was proposed. And this time, okay, it was discovered. It was Pluto, but Pluto was not the planet X because it was too small. The solution was just to change slightly the mass of Neptune. That time it was not known that well. So after it was refined, it turned out that everything is fine, and Pluto is just a coincidence. So no go. Yeah. The referee decided it was offside, right? VAR inspection and offside. No go. So it's 1-to-1. 1-to-1. Okay. So again, it was history, but this is some newer history. Current incarnation of this planet X. There were some reasons to think that, and still there are some reasons to think that there is some new planet undiscovered yet. And first, it was existence of some weird Trans-Neptunian objects like Sedna and this one here that were detached from Neptune. Their perihelion distances were significantly larger than the Neptune's orbit. They were strongly elongated, and it was not that clear how these objects should be formed. Yes, it was a theoretical problem how they were formed, and there was some proposition of yet another planet, quite large actually, of this same major axis. Well, until now, it was not detected, although it should be detectable. The next, let's say, characteristic of the Kuiper belt objects was some clustering of the arguments of perihelion, omega, around 0. There were some number of objects known, and their perihelions, their arguments of perihelions, they seem to be clustered around 0. They are Trans-Neptunian objects, yes, with the perihelion distance larger than 30 AU. And again, some planet was proposed, and a mechanism, Lidov-Kozai mechanism, was proposed to form such a clustering. Right? But it turned out that no single planet solution was found, and in order to keep all the perihelia in this order, there would be necessary to have more than one planet, no one planet, single planet solution. And there was another indication with the inclination of Kuiper belt objects of this same major axis, like 50 to 80, that they are inclined. And again, some planet was small planet like Mars was proposed. Its visual magnitude should be around 17 or less, quite detectable, but was not detected. Okay, but this the results. This planet 9 is best known. I'm run out of time. Is the work of Batygin and Brown, where they pointed out that there is not only the clustering in the argument of pericenter, there is also clustering in the longitude of the ascending node and the longitude of perihelion for large same major axis, like greater than 250 AU. And these are these points here, these green points. This plot is for the argument of pericenter, for the longitude of the ascending node, and for the this is so it was the longitude of perihelion. Okay, so there is some clustering, a few objects actually, not many, and they proposed that there is some additional planet, a super Earth. They proposed the parameters of its orbit, and they showed that it is possible to have this clustering, yes, to produce such clustering. These plots, maybe not going much into details, this one, the clustering, so the perihelions of these objects, they follow the aphelion of this hypothetical planet. So this is how we should read this. And they also noticed, actually people noticed it sometime before, that there are some objects called Centaurs whose inclinations are very high, like 90 degrees or even more, retrograde orbits. For semi-major axis here in between 30 and 100, and here perihelion distances inside, generally inside Neptune's orbit. So again, with this planet, this additional planet, they could explain how these kind of high inclinations could be formed. But after that, when more Kuiper belt objects were detected, the clustering is not that clear anymore. You see that this is this gray, dashed gray line here and here in both the panels. This is this original clustering reported by Batygin and Brown. Yes, but we see that there are also some objects here. Here, yes, the clustering around this point, but there are also points here. Not that clear. But in their recent paper, they suggested that the clustering may be still defended if we restrict somehow the parameters, like the perihelion distances of greater than 42 AU, so it's detached from Neptune, and not very wide orbits, like say major axis below 1000. So there is some clustering here. Maybe let's skip this. In the ecliptic plane, when we plot where are the perihelion positions, perihelions, we see that this clustering is not very strong. Actually, we see objects along the ecliptic at low ecliptic latitudes, which is understandable for observational bias. But in this limit of this new restriction on the parameters of Brown and Batygin, the clustering is slightly better. But okay, we can discuss if it is real or not. But in their recent paper, they performed many simulations showing, trying to say where this planet 9 should be on the sky, where to search for it. Yes, and they found out that here's the probability of the position of planet 9. It is most likely close to its aphelion and close to the galactic anticenter. And the distance is around 400 AU. It's the most likely distance. And the magnitude around 20. That they conclude that this planet could be detected with moderate telescopes or large telescopes. Okay, but no such planet was detected. Okay, so we are going to the last point. Yes, is there any other explanation of the clustering of orbital parameters? And there is a consequence of the modified gravity is the so-called external field effect, and this effect, it was actually postulated in this year already. If we have a mass body, and this is the vector field, yes, the vector field of its gravitation. The lighter is the color, the stronger gravitation. And if it is embedded in external field, let's say the vector field to the right, these arrows. In the Newtonian theory, it is simply a sum. We can add two vectors, two vector fields. Yes? But there is some region in which the acceleration is very low. And in one point, it is actually zero, exactly, it vanishes. But around this point, it should be there should be some modification of the gravity if MOND is true. Yes? And this is the effect of this modification on the gravitational field around the body is this external field effect, and it was shown that this can be important also for the outer part of the solar system. Okay, let's see. Again, we've got this modified Poisson equation, yes, and we write this is 4 pi g times physical mass density plus phantom mass density, yes, and we can compute the density of this phantom mass according to MOND for a system composed of a sun and galaxy, in which galaxy is treated as a point mass with the whole mass placed in its center. A simple model, it's quite fine here. And we see that around 5,000–6,000 AU from the sun in the direction of the galaxy center, there is this region in which gravity, Newtonian gravity, is very weak, and there should be this phantom mass. Yes? And we see with colors this phantom mass density higher here, zero at the position of the sun, as it should be theoretically, and this density, this zero here at these curves, actually the surfaces, because this problem is has rotational symmetry, and the density can be also negative. It's not physical mass. Yes, it can be positive or negative. But if we take this density and compute the perturbing acceleration, perturbing with respect to Newtonian acceleration from the sun, we see that there is some strong perturbing field. There are some lobes here with the perturbing accelerations of this order, like 10 to minus 11, and okay. So let's see what is the effect on the dynamics of Kuiper belt objects, right? This maybe very quickly for different alpha we can actually have different amount of this mass, different distribution, but maybe let's skip this. Let's skip this and see how the dynamics of a distant object looks like in the realm of this modified gravity. At this moment there is no perturbation from the giant planets, and also there is no motion of the center of galaxy in the ecliptic system, because you assume the sun is moving around the galaxy center. The center in the ecliptic reference frame, which is fixed, rotates, yes, somehow. But we don't consider it right now. It's only pure external field effect. And we see that after, by using the symmetry and after the averaging, no going into details, we obtain very simple system of 1 degree of freedom, and we can study its dynamics very easily. Here is an example: it's eccentricity and inclination in time. Okay, there is some oscillations, nothing really interesting in this case. But here it's, and in the plot on the right, E times cosinus, the argument of pericenter, and E times sinus of this argument, there is some evolution here. But when we take higher inclination of the orbit with respect to the direction to the, let's say, more, the orbit is here in this example more edge-on with respect to the direction of the galaxy center. The zero eccentricity orbit is unstable, and if we take a circular orbit, distant orbit, and which is initially in the ecliptic, and in this ecliptic, more or less, there is the galaxy center. Its latitude is around -5 degrees or so. We achieve strong excitation of the eccentricity, and this orbit of initially high value of the same major axis and perihelion distance, this perihelion can be brought into the inner parts of the solar system because the eccentricity grows. So even if the same major axis is 500 AU and the eccentricity is almost 1, the perihelion can be like 10 or 20 or something like that. Okay, so we see that this mechanism is actually quite important for the dynamics of the solar system. And here is just to say, maybe let's skip this. It is like the stability of this equilibrium, the circular orbit equilibrium. It depends on the inclination, as I showed. It also depends on the parameters of this transition function. When it is steeper, the transition function, it looks more like that. When it is smooth, it is more like that. So no effect of bringing distant objects into the inner part of the solar system. Just to maybe let's skip this. But when we add the other two effects, like the perturbation from the planets, here are they are treated in the secular way, averaged out, the perturbation is, and the fact that the direction to the galaxy center moves with a period of around 230 million years, so more or less the galactic period of the sun, we see that some initially with low eccentricity orbit, it can evolve in such a way, reaching very high eccentricities and so on. And here is the perihelion distance, it's just an example. So perihelion distances in the log scale, reaching the giant planets region here, Neptune and Jupiter. And here is the epochs in which galaxy in center is in its current position. So we record from one simulation only the positions, the parameters of the object, only after full revolutions of the sun around the galaxy center, because we want to compare with the observations. Yes, when the galaxy center is in some different position, this clustering may look differently. If this effect is important, yes. So only these epochs, and only when they are observable, so close enough to perihelion. And if we take this, we see that inclination also varies in the whole range. There is a longitude of the ascending node, longitude of perihelion, and we can make statistics of many simulations. Like here, it was like 600,000 initial orbits, and we record them only in these particular phases, only if we can see them. So more or less the perihelion distance below 80 AU. We see that the probability of observing object, this is for alpha, this parameter of the transition function of 2, we see this kind of plot. So first we see that the longitude of perihelion, the values of around plus 90 degrees or minus 90 degrees are prepared by the model. And so this is what we see, at least for high values of the same major axis. When we plot the observations, yes, observed objects, we have here 25 objects with same major axis larger than 250 AU. And we see that, okay, there is not, in observations, not that much clustering. And also in the model, there is not much clustering, maybe around 0 and 180, there should be more, but for wider orbits, there is this preference, and these objects, only 5 of them, this is what we got, they seem to follow this trend. And this is the rest of the objects below 250. But this plot, this picture, it depends on the parameters. If we change the alpha coefficient, so more steep transition function from Newton to Newton, we see that this probability map is looks like this, different. And again, these points can be somehow located in these arms. Again, here, more objects, but it is not that strong. More objects are needed, but it is the same for planet 9. Yes? See, it's not many objects. We can see that, maybe I will skip this. Okay. What are the model limitations? First is that we treat the perturbations from planet in a secular way, in a mean way. Yes, so this is the average. We average out the perturbation. So, and the perturbations are assumed to be small in order to use this theory, this model, secular model. Maybe it has some influence on the results. We see some other clustering around the longitude of ascending node. Also some preferences around plus or minus 90 degrees. And the most important plot is with the inclination. I'm almost done. Because this is something that bothered me for some time. Because here we have the probability of inclinations. This is inclination in the ecliptic reference frame. So we see only objects, also let's say, low inclinations. Yes, these are Trans-Neptunian objects, not the Centaurs. But according to the model, according to the simulation, there should be wide range of inclinations, actually the whole range, also retrograde orbits, but we don't observe them, and it was bothering me. We observe Centaurs with high inclinations, but they have perihelions inside the orbit of Neptune. But we don't see Trans-Neptunian, this detached from Neptune orbits with high inclinations. Okay, let's go to preliminary conclusions, because these are the conclusions from this Saturday, and on Sunday I changed my conclusions. I'm almost done. What is explained with MOND in the statistics of the observed Trans-Neptunian objects? First of all, it is explained why these objects, why we can observe these objects. Because yes, you see, you can have a wide orbit with distant perihelion, we wouldn't be able to observe this, but this mechanism can bring perihelions to our region of the solar system, and we can observe them. The statistics of the longitude of perihelion is quite well explained. High inclinations of Centaurs, also retrograde orbit, also quite well. But what is the problem? The lack of the orbits with perihelions beyond Neptune and high inclinations. This is the problem. This was a problem. And I used here, I wrote some rescue fields, 3 of them. Maybe model is too simple. Maybe we should wait to observe more objects. Who knows? Maybe we just haven't seen it yet. Or maybe there is a problem with MOND. This thing would be actually a good result too, right? Because it would mean that MOND is not right, because external field effect is a consequence of it. But this Sunday, I looked into the database, JPL, small body database, and I noticed that there are 3 new objects. Actually, I used to look at this database from time to time, hoping to find new objects, but this time I was lucky, because there were 3 new extreme Trans-Neptunian objects. all of them detached from Neptune. The perihelion distances are here on the right, Q, 70, 50, 60. And all of them are in retrograde orbits. Yes? And they are here. So they are not exactly where they should be. I haven't discussed all the details of the modeling because this gray picture, the model, what it says, it depends on many things actually, and it can be, I believe, quite easily modified in order to shift this border here. But anyway, it's a detail. It's a detail. So we know these three objects, which could be actually treated, maybe not formally, as a prediction of a MOND, because the model was first before. I'm speaking about this now. Okay, so this is the end and a conclusion. I wrote it in the title that searching for planet 9 is Experimentum Crucis, crucial experiment for the dark matter hypothesis, but actually it is crucial for both the hypotheses, because we could not only disprove dark matter, we could actually disprove MOND, right? So it is Experimentum Crucis for both of them. But okay, so let's see. First scenario, we find planet 9. We find it, and which is also important, just not to be the second Pluto, its parameters have to be sufficient to explain the observations. Yes, and if it is so, then gravity in the outer parts of the solar system is Newtonian because there is no room for external field effect, which is a consequence of MOND. And dark matter exists. And in the second scenario, when we don't find planet 9 and the statistics of ETNOs, first it has to be confirmed by detecting more objects, because still it is not enough. But first it has to be confirmed, and if it is still explained by MOND, with MOND, and there is no planet 9, it means that the gravity is Migronian, yes, because external field effect is a consequence of this modified gravity. And if it is like that, dark matter cannot exist, not only in the solar system, in galaxy, but in the universe. Yes? So this is what I wanted to say. Thank you.
Thank you very much. Thank you very much. Questions, comments?
Okay, thank you for your. I think the effects in our solar system are very subtle. But what about, let's say, power astro?
Actually, I expected this question. I expected that question, but I forgot to put a picture of bullet cluster. It would be easier to explain, to answer your question. Well, I haven't studied the bullet cluster, but I know that people say that it is some kind of a proof that dark matter exists, and that it is non-black. And this is that the dark matter is collisionless. Okay, this is what they say, but the dark matter. This is why they say that it confirms dark matter, because the picture inferred from the gravitational lensing. There is one cluster, another cluster, and there is this picture of the mass density inferred from the gravitational lensing. And this is like a proof, but it is like not normal situation. It was known before because gravitational lensing was actually used. MOND can explain mass in the clusters of galaxies. There is this problem, yes, I mentioned that there is still something missing, maybe by a factor of 2. But okay, I think that it is, in this point, it is nothing new from the bullet cluster. But what I think that they like, the authors like the most from this is that they say that dark matter is collisionless. because this gas that left after the galaxies, yes, they collided, passed through another, and there was inside some gas, yes, and they say there was this hot gas, but the dark halo was still around the clusters, and they say, okay, this is collisionless. Very nice picture. It is in agreement with the cosmological arguments and so on. Very nice. But phantom mass is also collisionless because it is not real. It simply follows the mass. We have real mass around this. This is phantom mass, which is not real. It cannot collide with anything. Yes. So it is in this case, yes, a bullet cluster is nothing decisive, in my opinion.
And about galaxies without dark matter.
Sorry, once more.
So-called galaxies without dark matter. So with velocity curves broken.
I don't know about this. I've heard about this, but I cannot say anything. Anything interesting about this. There is actually, just to put some light, this problem of dark matter, modified gravity. I've studied this for a few months only, so it is new for me. I don't know some details. You know, people in these different parties, they argue with each other and they say we have this argument, we have that. So they've been doing this for a long time. So it is not that easy to follow all the discussion. Yes? So yes, but I know that there are such objects. I cannot say anything now.
So you say that when planet 9 is not found, you will say that there is no dark matter. But when will you be able to say that planet 9 is not found?
Definitely. Yeah, sure. That's a good question. But definitely it will be before we can say that dark matter, this cosmological dark matter, is not found. This one is much more difficult to find that ordinary planet.
What type of planet would it be? I mean, would it be a gaseous planet?
This planet,
Earth-like planet?
this is
what would be its mass?
This is the mass. It is a few Earth masses. A few Earth masses. This range, yes. So it is, and it should be around 400 AU. So Brown and Batygin, in their recent year paper, they concluded actually that it should be detected. Well, it is detectable. Its brightness, its expected brightness, is within our abilities to detect. However, it is most likely in the galactic disk, in the opposite direction, in the anti-center, most likely there. So yes, there are some projects that they want to search for, find this planet. Yes, but well, you are asking when people give up on that, right? I don't know.
Because, you know, the point is that lack of evidence.
Yes, of course. But you see, it is yes, but it is shifting on some very huge problem of detecting exotic dark matter, of nature of which we don't know at all, to discovering an ordinary planet. It's like a few levels of magnitude in difficulties.
Not so ordinary, but still, I see the point.
Yeah.
Are there any comments on Zoom? I don't see hands being raised. You can only comment that we essentially need to find more Trans-Neptunian planets to verify your theory, which I like.
But it is exactly the same for Planet 9. They go on the same.
But wouldn't it be a stronger case if we find, like, you know, a couple of tens of Trans-Neptunian planets, so they follow your graph?
Exactly. For the it is true, but because for the Planet 9, they are also limited to 1000 AU, the major axis. So for values beyond this, maybe this planet would not be enough. Oh, okay, we can always introduce another planet, yes, planet 10. Oh, no problem, yes. So, but let's see.
Okay, thank you very much.
Like one more question.
Yeah.
Is there any reason why there should be like one planet line, or can it be like 10 small bodies?
I don't see any reason, any reason but this Ockman razor. Yes. It's only this. We don't know any reason.
Okay, thank you very much. Let's thank our speaker again.